In the realm of calculus, the concept of a limit stands as a fundamental pillar, underpinning our understanding of change and motion. Imagine approaching a destination, getting closer and closer without actually reaching it. This intuitive idea forms the basis of limits. In mathematical terms, a limit describes the behavior of a function as its input approaches a specific value. We denote the limit of a function f of x as x approaches a, as the limit as x approaches a of f of x equals L. This expression signifies that as x gets arbitrarily close to a, f of x gets arbitrarily close to L. To grasp this concept, consider a simple example. The function f of x equals x squared. As x approaches 2, f of x approaches 4. We express this mathematically as the limit as x approaches 2 of x squared equals 4. This means we can make f of x as close as we desire to 4 by taking x sufficiently close to 2. Limits, however, extend beyond merely evaluating functions at specific points. They empower us to analyze the behavior of functions near points where they might not even be defined, providing a powerful tool for understanding continuity, differentiability, and other crucial concepts in calculus. The profound significance of limits in calculus lies in their role as the bedrock upon which the entire edifice of this branch of mathematics rests. Calculus, in essence, delves into the study of change, and limits provide the precise language for describing and quantifying this change. At the heart of calculus lie two fundamental operations: differentiation and integration. Differentiation, which deals with instantaneous rates of change, relies heavily on the concept of limits. The derivative of a function at a point is defined as the limit of the slope of the secant line through that point as the 2 points approach each other. Integration, on the other hand, concerns itself with accumulating infinitesimal quantities. Here too, limits play a crucial role. The definite integral, which represents the area under a curve, is defined as the limit of a sum of areas of rectangles as the width of the rectangles approaches 0. Without limits, calculus would be akin to a language devoid of grammar, lacking the necessary tools to express its fundamental ideas. Limits provide the rigorous framework that enables us to define and analyze the concepts of continuity, derivatives, and integrals, forming the very foundation of calculus. The derivative of a function, a cornerstone of calculus, quantifies the instantaneous rate of change of that function. Imagine a car accelerating along a highway. The speedometer displays the car's speed at any given moment, representing the instantaneous rate of change of its position. In calculus, we define the derivative of a function f of x at a point x equals a as the limit of the difference quotient as h approaches 0 f prime of a equals the limit as h approaches 0 of the quantity f of a plus h minus f of a, all divided by h. This expression represents the slope of the line tangent to the graph of f of x at the point a f of a. The difference quotient measures the average rate of change of f of x over the interval a to a plus h, and as h approaches 0, this interval shrinks to a single point, giving us the instantaneous rate of change. The definition of the derivative using limits captures the essence of instantaneous change. By analyzing the behavior of the function over infinitesimally small intervals, limits allow us to precisely quantify how a function changes at a specific point. The intimate connection between limits and differentiation lies at the very heart of calculus. Differentiation, the process of finding the derivative, relies fundamentally on the concept of limits. In essence, the derivative is defined as a specific limit, the limit of the difference quotient as the interval over which the average rate of change is calculated shrinks to 0. This relationship is not merely a matter of definition, but reflects a deep conceptual link. The derivative embodies the instantaneous rate of change of a function, a concept that inherently involves approaching a point without actually reaching it. Limits provide the precise mathematical framework for capturing this idea. To illustrate, consider the function f of x equals x squared. Using the definition of the derivative, we find that f prime of x equals 2x. This tells us that the instantaneous rate of change of f of x at any point x is twice the value of x. The derivative, derived using limits, provides a powerful tool for analyzing the behavior of functions and understanding their rates of change. Section 5. Illustrative examples, limits and derivatives in action. To solidify our understanding of limits and derivatives, let's explore a few illustrative examples. Example 1. Consider the function f of x equals 2x plus 1. To find the derivative, we use the definition f prime of x equals the limit as h approaches 0 of the quantity 2 times the quantity x plus h plus 1 minus the quantity 2x plus 1 divided by h. This simplifies to the limit as h approaches 0 of 2h divided by h, which further simplifies to the limit as h approaches 0 of 2. So we get 2. Thus, the derivative of f of x equals 2x plus 1 is f prime of x equals 2, indicating a constant rate of change of 2. Example 2. Let's examine the function g of x equals x cubed. Applying the definition of the derivative g prime of x equals the limit as h approaches 0 of the quantity x plus h cubed minus x cubed divided by h. This simplifies to the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed divided by h, which further simplifies to the limit as h approaches 0 of 3x squared plus 3xh plus h squared. So we get 3x squared. Therefore, the derivative of g of x equals x cubed is g prime of x equals 3x squared, demonstrating a rate of change that varies with the square of x. These examples showcase how limits underpin the calculation of derivatives, providing a powerful tool for analyzing the behavior of functions. Section 6. Applications of limits and derivatives. The concepts of limits and derivatives extend far beyond the realm of theoretical mathematics, finding widespread applications in various fields. 1. In physics, derivatives are indispensable for describing motion, velocity, and acceleration. For instance, the velocity of an object is the derivative of its position with respect to time, while acceleration is the derivative of velocity. 2. Engineers rely heavily on derivatives in areas like structural analysis, fluid dynamics, and control systems. Derivatives help analyze stress and strain in structures, model fluid flow, and design control systems for various applications. 3. In economics, derivatives play a crucial role in optimization problems such as maximizing profits or minimizing costs. Marginal analysis, a fundamental concept in economics, relies heavily on derivatives to analyze the impact of small changes in production or consumption. 4. Limits and derivatives find applications in computer graphics, image processing, and machine learning. For instance, derivatives are used to detect edges in images and optimize algorithms in machine learning. These examples highlight the pervasive influence of limits and derivatives in various disciplines, demonstrating their practical significance in solving real-world problems. Section 7. Common misconceptions about limits. Despite their fundamental importance, limits often become a source of confusion for students new to calculus. Let's debunk some common misconceptions. First, a limit is not the same as a function value. While a limit describes the behavior of a function, as its input approaches a value, it doesn't necessarily equal the function's value at that point. A function can have a limit at a point where it's undefined. Second, a limit can exist even if the function is undefined at the point. Consider the function f(x) equals x squared minus 1 divided by x minus 1. This function is undefined at x equals 1, but its limit as x approaches 1 exists and equals 2. Third, limits don't always exist. Not all functions have limits at all points. For example, the function f(x) equals sin of 1 divided by x oscillates infinitely as x approaches 0, and its limit at x equals 0 does not exist. Understanding these common misconceptions can help students develop a clearer and more accurate understanding of limits. Section 8. Mastering limits. A stepping stone to calculus proficiency. Mastering the concept of limits lays a solid foundation for success in calculus. Here are some tips for developing a strong understanding of limits. First, embrace the intuitive idea. Start by grasping the intuitive notion of approaching a value without reaching it. Visualize limits graphically and relate them to real-world examples. Second, practice evaluating limits. Work through numerous examples involving different types of functions and limit situations. This practice will solidify your understanding of the algebraic manipulations involved. Third, understand the formal definition. While the intuitive understanding is crucial, delve into the formal epsilon delta definition of a limit to gain a deeper and more rigorous understanding. Fourth, connect limits to other calculus concepts. Recognize how limits underpin derivatives, integrals, and other key concepts in calculus. This interconnectedness will enhance your overall comprehension. By diligently honing your understanding of limits, you equip yourself with an indispensable tool for navigating the intricacies of calculus. Section 9, Conclusion, the significance of limits in calculus. In conclusion, limits stand as an indispensable pillar of calculus, providing the precise language for describing and quantifying change. They form the foundation upon which the concepts of derivatives, integrals, and continuity are built, enabling us to analyze the behavior of functions in profound ways. From physics to engineering, economics to computer science, the applications of limits and derivatives extend far beyond the confines of theoretical mathematics, impacting our understanding of the world around us. By mastering the concept of limits, one embarks on a journey into the heart of calculus, unlocking a world of insights and applications.